This is a Lego skyscraper simulating a major earthquake. And this is that same Lego skyscraper after 2 weeks of engineering. But what makes this one so stable? To find out, I spent the last month building 3 Lego skyscrapers to not only test on my Lego earthquake simulator, but also to test some of the systems and techniques engineers actually use to make skyscrapers safer. But before I can test that, I need to figure out how earthquakes actually work. So I reached out to the United States Geological Survey, and they were kind enough to give me a tour of their facility in Colorado. And this is where I learned that not only do they have thousands of seismographs all over the world measuring for seismic activity, but they also have analysts working 24/7 around the clock to track that seismic data and publish it to their website. This is William Yeck, and he explained to me what causes earthquakes and how they're able to track them.
Yeah, so I mean, broadly, the Earth is made up of these tectonic plates that are moving around, and they rub against each other in different ways. They can be pulling apart from each other, they can be sliding across from each other, so we call that transform, or they can be converging. And usually in converging, one is subducting below the other one. And at these tectonic plate boundaries, you build up stress, and the Earth at a fault will lock, and it just locks and it builds up stress, and then it releases. Just this elastic release of energy, and that elastic release of energy is quick and it causes shaking, and that's what an earthquake is.
To make this a little easier to understand, we can take 2 Lego base plates and start slowly pushing them into each other, building up the pressure, causing them to bend and creak until finally all that pent up energy releases. And this massive release of energy is known as the focus, and all that energy from the plate slip will radiate out from the focus in waves.
What we can see here, this is the P wave right here. So this is the first arrival, the body wave, and then this is the shear wave, which I said was larger often. These earthquakes have this very characteristic shape where there's this first arrival and a second arrival close in. And as you get further and further away, the separation of that P wave and that S wave gets larger.
And what he's talking about here is actually the energy waves that travel through the Earth. And all we have to do to see those is take those same Lego base plates from before and snap them underwater. Okay, so you can't see it as well with the base plate, but if we drop something in the water, this simulates the same thing. You can see the ripples that spread from the focus. And these are the same massive waves of energy that cause streets and buildings to shake. But how do we know how strong these waves actually are? Well, that's where a seismometer comes in.
This is a seismometer. These actually measure velocity, but they're very sensitive. We can record, say, a magnitude 5 earthquake on the other side of the globe with these at a quiet enough station. So they're extremely sensitive. We bring in about 2,300 seismometers, so we can detect them really quickly and report on them very, very quickly.
Thank you, man. That's great. I appreciate your time.
Yeah, happy to do it.
And since we're going to be simulating some pretty intense earthquakes, I want to try and build a seismometer myself. Turns out a basic seismometer is pretty easy. You just need a spool of paper and some sort of marker. So as you can see here, I built up a pretty primitive seismometer just using a marker, and this is just connected on a hinge with a few rubber bands so it'll swing back and forth on our paper, which I've gone ahead and spooled with a Lego motor and worm gear, which will gear it down just enough so we can spin slowly and we can get some precise markings. Now we just have to test it out. And to test all the buildings in this video, let me introduce you to the Lego Earthquake Simulator 2.0. See what this can do. Here we go. Level 2. This thing's gonna be fun. So if we throw this guy on here like this, all we gotta do is lock it down, lower our little marker into place. And as you can see, if we start running this guy slow, the paper will move from one side to the other. And then we can just start our earthquake simulator, and you can see it's gonna capture those vibrations on the paper, which is pretty cool. And then if we go really crazy, you can see how crazy the lines get. Let's turn this guy up. Now, while this is working really well, this thing is also only moving in one direction, right? Side to side. So we're basically only getting a 2-dimensional measurement. But that's a pretty easy way to build one, and this is how seismometers actually worked before they went to digital. However, since this is a little large, and it'd be a bit hard to have this on the table while we're shaking the buildings, I'm gonna swap this out for a small digital seismometer, and we can connect this to the back of our earthquake simulator here. And the great thing about this one is we can stream all the data we're getting right to our computer. And this thing gets pretty powerful too. Look at that. That's still only on the low setting. And I'm gonna be building 3 different skyscrapers using different engineering methods to test out if they'll actually work or not. But before we do that, we need to put this thing through its paces and see if it actually works. First up, we have our tall building. Here we go. Started off mild. Number one's gone. Now let's try that same thing out on a shorter building. Hey, that's pretty good. That's not even max speed though. Wow, that one's gone too. So far this thing's working pretty good. Let's try something a little bit beefier in 3, 2, 1. Here we go. Dang, this thing shows no signs of quitting. That was awesome. Which means this thing is finally ready for our giant Lego skyscrapers. We just gotta build them. Slap this guy on here. And now we have our second floor. I'm gonna minimally design the floors on each of these levels, but I am gonna put furniture and people in there to see the effects the earthquake would actually have on the interior of the building. All right, let's keep building this up. This is our first skyscraper with no additional support. For each of these skyscrapers, I'm gonna build them a bit more earthquake sensitive. So for this one, I've only overlapped the bricks every 8 or 9 layers. That way, as you can see, you can push in some of the pieces. That way we can really see how much better this will stay together when we actually add the earthquake proofing technique to the end. And as we know, you can't actually make something earthquake proof, but we can minimize the damage to the structure. But before we go crazy with the earthquake engineering on this, let's first test it out like it is to see what we're working with. Here we have our first skyscraper. As you can see, I decided to go pretty simple with this one. We have 2 floors here. The one at the bottom is empty, but this one up here is set up like an office, so we got a bunch of minifigures in there, and we got a camera so we can see what happens to them. So first we're gonna test this out without adding anything, and then we're gonna bring it back to life and test it again. We'll start off a bit slow here. Okay, it's shimmying. Moving it back and forth. Getting some small waves here, bring it up a little bit. Oh, we're losing some people there. There it goes. That. It's moving quite a bit. Okay, so it's made it through the first level. Now what I'm gonna do is move it up to the second level. This is as hard as this thing can go. Let's see what happens. Oh no. Getting some real wobbles now. Dang! We are getting some breakage at the back of the wall here. Oh no! Oh no! Wow. Well, there it goes. So as you can see, with nothing added to this, the building wasn't able to do anything to remediate the vibrations from the ground. Now, given that was like level 2, it already performed pretty well, but the shakiness up top was crazy. So for this next one, we're gonna test it on level 1 and see if we can get the building to stay completely sturdy. And for this one, I'm gonna use a technique called a base isolation system. Essentially how this works is the building is placed on flexible bearings or isolators, usually made up of layers of rubber and steel. And these actually absorb the seismic energy waves that go through the building, effectively disconnecting the building from the ground and reducing shaking by up to 90%, which is crazy good. So we're gonna take this and put it on some bearings to give it a little bit of wiggle room. And my first idea to make this in Lego is just to use some of these special rubber Technic pieces they make and kind of just link a couple of these together between 2 plates to create a flexible isolator. Now you can see we have this flexible stick just like that, and this thing can go between 2 plates to hopefully keep our building up. And I actually used a similar design to this when I tested Lego houses on my earthquake simulator, but the problem was they could only go one direction, so I'm not sure if that's bad for this, because these guys can only move back and forth, and if the earthquake is going this way, it's pretty rigid. Look at that thing, that's weird. It is flexible though, so there's that.
Yeah, I don't know, guys.
So these are not going to work. These can obviously just go side to side, but if we use a bearing system with a couple of these curved tiles here, we should actually be able to give it a little bit more wiggle room. So let's try building up a few of those. So now we just gotta build up 4 more of these and put them under our skyscraper, and those should act as our base isolation system. It's just so incredible to me that something so simple works this well. Like, look at how stable the top is. As you can see, an object at rest stays at rest. So check it out, guys. Now, as you can see, we put this on top and we shake the bottom. Look at how stable the top is. And if we put a weight on this, or like this cup, for example, it's like completely sturdy. That is incredible. And it's just so simple. It's just bearings that allow it to rotate just a little bit. So here we go. We're gonna test out these base isolators. I'm excited to see what this does because the first time we tried this out, it didn't end very well. We're gonna just start this slow and then we'll speed it up to full speed. In 3, 2, 1. All right, we're going. Making noises, a little faster. No way, dude. That's insane. Oh my gosh. Literally nothing has fallen over on the inside. Check it out. I am like so extremely impressed at how these things work. Just keeps the entire thing upright. Like you literally can't even tell this is moving. Look how much the floor is moving. Look at that. That is crazy to watch, actually. You can kind of see the ball bearings in there just moving around, sliding back and forth. I only put 4 in each one. I definitely call a base isolation system a complete success. It works really well. That's really impressive, actually. So let's test the next one. For skyscraper number 2, I want it to be shaped like an octagon. So I'm gonna lay down the base using some of these hinge pieces to let us get the angles that are gonna allow for the octagon shape. And we're gonna have to inset that in about a half plate using jumper plates just so we can get the correct dimensions so the hinges will all connect. Since we want to keep locking it together, we're going to take another layer of these hinges on this next level and snap them in to lock down the corners. Now we should take our fancy hinge bricks and perfect. Look at how much that alone shows this guy up. You can see right here what I've done is even use some slopes to kind of give it a little bit of a wider shape here towards the bottom. Check it out, looks pretty good. So then what I'm gonna do is up here actually taper it in and build a square in the middle that goes up pretty high. A lot of skyscrapers actually use this and it's called a setback, essentially just making it smaller and smaller and tapering it in as you go up to the top, which gives it more structural stability the higher up you get, which you really need. Once I add the top part to this, our second skyscraper will be finished and we can test it out. For our next skyscraper, I built this monstrous 115 brick tall skyscraper, and it has 3 floors. We have the lobby down here, and just like our last one, we'll add some furniture in there and a camera so we can actually see what's going on. And then for our second level, I actually angled it by 45 degrees and connected that with some jumper plates to give it a bit more visual interest. Then we have our third floor, which is pretty small, and the spire at the top. And all this part on the bottom floor is just made in 8 really tall sections, only locked together at intervals, like our last one, to make it really earthquake sensitive. I get a little nervous after I build each one of these thinking, man, this could crush me if it falls down. But it's really not that heavy, so I don't know what I'm really worried about. But before I show you guys how this thing actually does, I want to quickly tell you about this. It's called a stud measure, and I designed it specifically for Lego builders to be able to better measure their creations. It has a double-sided tape, so it measures in both bricks and studs. And with its custom fit end piece, it snaps right between the studs so you can measure easily. It's the perfect tool for any Lego enthusiast that's ready to take their building to the next level. So to get one for yourself, you can go to studmeasure.shop or click the link in the description. Here we have our second skyscraper. This one, pretty straightforward. There's not a lot of stability put into this. I really do want to see it crumble and then see the difference when we actually add the stuff to it. And by the way, for all of these, I'm trying to keep it as similar as possible with the controls. We have a GoPro down here in the lobby to see how the people in there will fare, and we're ready to go. Let's test this thing out. Here we go. They're moving. We're just gonna keep it coming. Look at it moving. We lost this entire front of the building. I can't believe it's still upright. Here we go. Uh-oh. No way. That was pretty cool to watch. You can see once that first panel on the front went, the whole thing just kind of dissolved over to one side. So yeah, that's how that one fares. Let's see if we can make this thing even better. To re-startify this building, we're gonna use two methods. The first of which is called shear walls. It's just a wall we're gonna build in the very center of our skyscraper, which will hopefully shear it up and minimize the lateral movement of the building. So for that, we're literally just gonna build a giant 8x8 pillar in the middle of our skyscraper. And we're gonna use 2x4s interlocked in a running bond pattern to make it as sturdy as possible. In fact, we're gonna go 10x10. And if you think about it, this actually makes sense because you're creating a really strong, solid pillar all the way through the building, and they'll make these out of concrete and rebar, but these will be super thick. And you know what would be really smart actually, is if we ran Technic vertically through this to simulate like rebar or like steel. See there, we have that. And then we build around this guy. So this will go all the way through the layers. And we'll kind of interlock it with some Technic bricks as well. This goes in here. And then we just add a few more thinner ones for the other floors. And then the second thing we're gonna add to the skyscraper is something called cross bracing. The cool thing about cross bracing is it utilizes geometry to actually create a stronger structure. And so what I've done inside this guy, if I just take it apart again, is on each of these four sidewalls, I've added a bunch of Technic axle bricks. So what we're actually gonna do is take two of these Technic lift arms and cross them over like this, to create a little X shape. And then the really smart thing about this is it's repeatable, so we can just continue making a bunch of these and snapping them into those Technic bricks all the way up the walls. And the reason we're gonna use triangles for this is it's a lot stronger. And you can see that if you create a linkage mechanism using 4 lift arms, when you press down on the top of it, it's actually extremely weak, because all the points where the lift arms attach to each other actually act as hinges. But if you take some of those same lift arms and create a triangle shape, where they're all linked into each other, none of the connections are able to hinge, creating an extremely strong shape when you press down on it. And that's the same thing we're gonna do on the base of this skyscraper. So here we've added all the shear walls on the inside. So we have one here, one tall one, another one here, and that just goes all the way up. We've also added the cross bracing on 4 of these 8 walls down here, just where we can fit it in. And we're gonna test this out. We're gonna try and keep it as similar as possible. Here we go. Start her off here. Going a bit slower. Okay, seems to be doing good. Not terrible, not terrible. Test it out. Maybe get it going a little faster here. The walls are definitely holding up better. And that's full power. So as you can see, this definitely works way better than it did without any reinforcing at all. I think the shear wall definitely helped down for this bottom section because it seems a lot sturdier. And then up towards the top here, there were honestly only 4 studs of connection, so that wasn't the smartest thing. But this thing definitely worked out a lot better than with nothing at all. And we were pushing that to almost its max. And as you can tell, the people on the inside made it out because this thing didn't crumble on top of them. So I'd call that a success. Shear walls and cross bracing definitely work. This next one is gonna take a lot more engineering. I think it's gonna work out a little bit better. For our third skyscraper, we're gonna go even bigger. Measuring in with our stud measure at 48 studs wide. For this one, we're gonna need a lot of windows. So I'm doing a little work on the front of this here, and I've really just decided, I think having these little slots between the windows looks good, but it's a little too much white. So I'm gonna instead use dark bluish gray, and then for the floor color for each of these levels, I'm gonna use that same gray. And I'm gonna make this thing over 5 stories tall. These are just some of the design decisions you have to make early on, because replacing all that when you get to the top is not the most fun thing. On this first level, as you can see, we have a nice little lobby. I'm gonna add a brick wall here with a desk. We're gonna add a few cameras into this one so we can actually see what's going on the inside. But now that we finished planning the first level, we just have to duplicate that 5 more times. And this level is 16 bricks tall. For our last skyscraper, we're gonna test out something really cool called a tuned mass dampener, which is a type of oscillator that's typically suspended from the top of the building to sort of counteract the swaying motion. And they can actually tune these things to match the frequency perfectly so that the building's shakiness is minimized. For example, there's one of these in Taipei 101. It's their famous golden damper, and it weighs approximately 660 tons. And since that giant thing is able to reduce sway by up to 40%, I really don't see why we can't try the same thing here. Because all we really need is just a giant Lego ball. And then we can build a Technic structure in the top of this with a tuning system to suspend it from the top. The thing is though, we're gonna need to make this ball up to 10% of the building's weight, which as I've calculated is around 40 pounds. So I'm gonna start building up a Lego ball out of yellow pieces that we can fill with weights to act as our TMD. And since this will basically work like a pendulum, we're just gonna build a tightening system at the top so that we can tune it to better match the frequency of the building swaying back and forth, or also known as the fundamental period. So here inside this, we have our tune mass dampener. And there's actually two ways we can tune this to make it match the fundamental period of the building. So as you can see, it's just a big 4-pound ball that swings back and forth, but I've connected it to these gears up here. And right now, the gears aren't attached to anything. So when we swing it, line it up like that. Watch how long it takes for it to stop. Okay, that's how long it took to stop with no tuning. So now, if we add one of our friction gears here to this gear, it'll tighten up the hinge so that it slows down a bit. So if we push that same amount, and we can also extend or shorten the lift arm that's connected to this ball to change the length of the pendulum, which will give us another aspect of control. At this point, I'm just hoping this will actually work on top of our giant tower. But we got it finished up, so let's test it out. All right, guys, this is it, our final skyscraper. We're gonna test it first without our TMD, and then we're gonna add that in to see what kind of difference it makes. And to do that, I'm also gonna take off this little seismograph down here, put this up at the top. To make this as accurate as possible, I'm gonna try and simulate the same earthquake twice manually, just so we can get kind of a feel for how this thing's working. So this is without the TMD. Moving a little bit. You can see we get the high-speed wobbles going. Look at that. We can give it a little pulse. And it's shaking. And give it a little more. As you can see, the building's shaking pretty bad, but we can also switch this out and test it on level 2. There's some high-speed wobbles. Just look at the size of the waves we're getting. All right, so now let's add in our TMD and see how much that changes it. Here we go. Look at that. I think it's kind of working. You can see the pendulum at the top is swinging, so it's keeping the building up straighter. That's really interesting. It's interesting how the slower you go, the more it swings. Wow, honestly guys, I can't tell with this one. I really am not sure. It's hard without comparing the footage right in front of me, but you can see this in comparison to the first one. While this may be cherry picking a little, here's an example where the speed almost matches perfectly. And you can see the dampener actually working how it's supposed to, slowing down the building. It just wasn't reliably consistent because I lacked the scientific know-how to tune it properly, which in hindsight I could have put more effort into, but it is still cool to see it working right here. I think overall it's really hard to tell in person. It's also really hard to tune this thing just with those 4 gears, which I thought would be a lot easier. I don't know if you guys can see a difference, comment down below. So while all these systems do work to minimize the damage from earthquakes, most structures survive with minimal damage, and that's because of the scientists and engineers working together to ensure we have the safest buildings possible. Earthquakes happen every day all around the world. And while we can utilize physics and science to minimize the damage they do, they're still very real and very dangerous.
Still going.
We still have a skyscraper standing, and that's a problem.
So next time you look at the skyline, I hope you'll remember all the cool engineering that goes into making them safe.
See you in the next one.